Hi there. In this video I'm going to talk to you about some revision material related to expectations, expected values of random variables, and the idea of conditioning. And at the end I'll introduce one new idea, well I think it's new, that will be important in the subject and that we'll revisit in lectures as well. If you would like to read more about what I'm talking about here in this video, you can take a look at a couple of sections in the recommended book, the Stock and Watson book. A lot of it is stuff that you have seen before, certainly in first year, and I've put the relevant QM1 lecture notes on the LMS for our subject so that you can refer back to those and refresh your memories about expected values and things like that. We will use these ideas throughout the semester, so if you think it would be helpful, if you find yourself being a little bit rusty on that stuff, it would be good to refer back to those QM1 notes. You'll find them familiar. And of course we'll have our own notes as we go along on this material. We'll start here with the idea of an expected value. An expected value is by definition taken of a random variable, and it consists of an average. The expected value is an average or a mean, and it consists of an average weighted by the probabilities of all of the possible outcomes that the random variable can take. The mathematical form of that averaging is a bit different depending on whether we have a discrete or a continuous random variable. These are the formulae just taken directly from the QM1 notes, for example. And you can see that in either case we're taking a sum or an integral of the y representing the possible values, the lowercase y representing the possible values of the uppercase y, which is the random variable, weighted by the probability mass function or probability density function, as the case may be. Okay, so that's the definition, just reminding you what that is. Now, we're actually not going to use that definition from now on. So if this were a probability course, then I would start giving you some probability distributions and ask you to work out some expected values. But this is not a probability course, it's an econometrics course. But you should at least be aware of what is the basic definition of this mean. Okay. Now, we want to talk about statistical inference. That's what econometrics is going to be all about for us. And in statistical inference, we think of this expectation of the random variable y as being the population mean of y. Okay, and it's going to be important for us to remember all the way along that it's a population mean when we see this expectation. Okay, not something that we observe, but something that we want to estimate when we do statistical inference on the basis of a sample. Now, here's an example that I'll mention a couple of times as we go along. Y might represent adult height, by which I mean you can imagine drawing at random an adult from the, let's say, the Australian population and measuring how tall they are. Okay. Now, on average in Australia, adults are 168.7 centimetres tall. That's a statistic taken from the ABS. There's a link there if you want to follow it and take a look at the source for that statistic. So that's we could take that as being the population mean. And one thing I want you to take from that is not so much the number itself, but just to emphasize that the expected value of a random variable is always a single number. In this case, we know what that number is. More generally, we don't know what that number is, and we try to estimate that number with a sample statistic. Now, that's interesting as far as it goes, but a far more interest in econometrics is the idea of conditioning and the idea of conditional expectations. This is where we start to get at the idea of relationships between two or more random variables. So let's suppose we have two random variables, x and y. The conditional expectation is also a mean. So if we take the expected value of y, conditional on the random variable x, taking some value little x, what we mean by this is that it is the average value or mean value of y when we know that the random variable x takes this specific value, lowercase x. And just notice this kind of uppercase, lowercase kind of distinction here. We will try and stick with this throughout the semester. So an uppercase letter is representing a random variable, while a lowercase one is representing a fixed value that's not random. Okay, oops. Okay, so this is the population mean. So it's got an E, so it's still a population mean of y, but with the additional piece of information that we want to work out the mean of y when we know that x takes a particular value. And if there is some kind of relationship between y and x, then this is interesting. Now, remember the unconditional mean of y was a single number. The conditional mean of y is a function of x. As we vary the value of x, in general, we can get different values for the mean of y. So that's what we mean by a function. Okay? Different values for x correspond to different values for the mean of y. For example, for adult height in Australia, we could have y as remaining adult height, and x here is the gender, male or female. Okay, so the average height of males in Australia is 175.6 centimetres, and for females it's 161.8 centimetres. So clearly, by knowing whether we are talking about males or females, we have more information about the possible values for y than if we didn't know whether we were talking about males or females. So conditioning on a random variable can give us more information about another random variable. So here's how we can write this in mathematical terms, if you like. We define this x random variable as being 0 for a female and 1 for a male. Okay, so imagine we draw an individual from the Australian population at random. Then there will be a random variable x, which assumes the value 0 or 1, depending on whether that individual is female or male. And then there will be a height measured for that person as well. We can represent these two separate means that we have for males and females in the form of a single equation then that looks like this. Okay, the average population mean of y conditional on x looks like this. 161.8, which is the value for the female, plus 13.8, which is the difference between these two numbers, times x. So when x takes the value 1, we will get the expected value for y is equal to 161.8 plus 13.8, which returns that 175.6 number again. Okay, so this conditional mean that we've written down here is exactly a population regression function. Okay, so this thing here is like a regression. Well, it is a regression on a dummy variable, something that you've seen before in second year, for instance. Okay, so throughout our subject, we will treat these kinds of conditional expectations of y given x as being basically identical with a population regression function. Okay, a population regression function is a conditional expectations function. We can use the terms essentially interchangeably for our purpose. All right, that's all the population stuff. So when we talk about regression models, we talk about population stuff like this. Okay, in general, we don't know what these coefficients are. Okay, so those E's represent population means. Now what we want to do in statistical inference is write down a model, maybe in the form of a conditional mean like this, and then estimate that conditional mean using a random sample. For example, if we want to estimate a population unconditional mean, then we could use the sample unconditional mean. So this is just the usual sample mean, y bar will often denote it. In this case, to try to just really make clear the links between the population and sample quantities, we've got to put a hat over the top of any population quantity that we're estimating using a sample. So in this case, we are estimating the population expectation with the sample expectation. So I've put a hat over the top, and that's the sample mean. Similarly, when we're talking about a regression or a conditional mean like this, then we can write down a sample regression function, which is the thing that you estimate on the computer, right? So here we have an estimated regression. We've just put some hats now. So that reflects once you see the hats on there, they're the sample things, okay? There will be numbers there on the basis of the data that you've estimated. And so we put a hat on this E as well. So this is the estimated regression function, or the sample regression function, estimated by OLS usually. Okay, so the important thing there is just to keep your mind on the notation that we're using. When you see hats, you know that we're talking about samples that we've observed and calculated. And if you're not seeing the hats and you're just seeing the E's and the random variables, then we're talking about populations and models. Okay, we need to be able to switch between those as we talk about all of our methods. All right, a few properties now that allow us to deal with these expectations operators. First of all, just a simple one for unconditional expectations to get warmed up. We have, let's suppose we have n random variables, y1 up to yn. So those can be any random variables. Obviously, we're thinking of those as being relevant to our sample, our statistical situation. And then we also have some constants, and they're lowercase, a1 to an. Okay, they're not random. So they're just some numbers of some description, okay? But they're not random variables. So if we then consider a weighted sum of these random variables using those a's as weights, okay, so this formula here is just saying to add up ai times yi. And if we take the expectation of that sum, then the expectation can come inside of the summation, and the ai, which is constant, can come outside of the expectation. Okay, so this linear property of expectations has kind of two things going on. The linear part is actually that the expectation can come inside the summation, and then in addition to that, these constant weights can come outside of the expectation as well. Okay. Now that has an easy, immediate application in showing you a result that you've seen before. You know this, but just to remind you of how you show that the sample mean is an unbiased estimator of the population mean. So a sample mean, as we've just seen, looks like this. Y bar is 1 over n times the sum of the yi's that you've observed. And we can think of this as being one of these weighted means. Okay, we can think of it as being a weighted mean where these weights are the same for every I. The weights are 1 over n for every I. So this fits within this linear property of expectations right here. Okay, and 1 over n is not a random variable. You know, when you're doing statistics, you know what n is. You know what your sample size is. Okay, so that's a constant. It's not a random variable. Now, let's suppose that the population mean is indeed constant and equal to mu for every one of these i's. It then follows that the linear property of expectations gives us the unbiasedness of the sample mean. So an estimator is unbiased if its expectation is equal to the true population parameter. In this case, it works as follows. We have the expectation of y bar, and we would like to show that this is equal to mu. Okay, here's our population parameter. So the expectation of y bar is equal to, and now we apply the linear property of expectations immediately. When we take the expectation of this quantity, the E comes through the summation and through the 1 on n, because that's a constant, and we've just got the expected value of yi, which is equal to mu. And so we're just adding up mu n times, dividing by n, which cancels out and leaves us with mu at the end. So the sample mean is an unbiased estimator of the population mean. Okay, so simple result, but a good bit of practice for using that linear property of expectations. All right, conditional expectations now. We'll use a lot of these as we're understanding how regression models and other models work, so this is going to be important. We'll get plenty of practice. The first property of conditional expectations is quite a simple one. Let's suppose we have A and B, they can be any old random variables, and X can be any old random variable as well. And this first property is simply saying that if we take a conditional expectation of a sum of two random variables, A plus B, then that is equal to the sum of the conditional expectations taken separately of A and B. Okay, so this is just the same as unconditional expectations. Okay, expectations are linear operators. They can go through sums and be taken separately like this. And that can be extended. You know, if we had lots and lots of these random variables and we're adding them up, then we can take the expectation inside that summation as well. Now, another important property is this one. If we take the conditional expectation given X, so conditioning on X, if we take the conditional expectation of anything, any random variable involving the X's alone, then in the process of conditioning on X, we're treating X as being known, as being not constant, as being constant within this expectation here. Okay, so the expected value of f of X is f of X. So by saying conditional on X, we are saying we know X, and therefore there is no averaging to be done. It gets treated as a constant. Similarly, if we have a slightly more complicated expression like this, like the expected value of f of X times y, where y is some other random variable, conditional on X, then the f of X continues to get treated like a constant, and it comes outside of the expectation. Okay, so when I'm saying we're treating it like a constant, this is the same as what we saw back here. Okay, when we have an unconditional expectation and we have these constants, the constants can come outside of that expectation. And with conditional expectations, what I'm saying is the same thing happens. When we condition on X, those terms that have X in them can come outside of the expectation. In addition to that, if there's any constants in there as well, then they have the same property. So the expected value given X of a constant is the constant itself, and the constant can be taken outside of the expectation in a more complicated expression like this. Alright, so with those properties in mind, we can deal with a regression model, or we can derive a regression model on the basis of an equation that looks like this. And this kind of operation we're going to do quite a bit in the first part of our subject. So here is an equation, a causal equation, by which we mean that we're looking at individual wages in this equation. And they are being influenced by, among other things, the amount of work experience that an individual has. Okay, now it's very common in practice, and we'll return to this, I won't dwell on it now, but it's very common in practice to model the effect of work experience on an individual's wages as being a quadratic. Okay, it's not a straight line. Basically, the idea is that the initial years of experience when you enter the workforce allow you to learn a lot, increase your productivity a lot, and as a result increase your wages a lot. Okay, so the early years in the workforce correspond to high rates of increase in wages. But the longer you're in the workforce, the rate of increase of wages slows down, and that is captured by this kind of quadratic functional form that we have here. Okay, now it's quite common in a regression to have this disturbance satisfying an assumption that looks like this. This is the standard assumption, which is the conditional mean of the disturbances given the explanatory variable is equal to 0. Okay, so that's our equation. If we want to take that equation and write it in the form of a conditional expectation of wages given experience, then this is what we do. The regression function that we want is the expectation of wages given experience, which means we're going to take the expectation of the right-hand side of this equation up here, conditional on experience if we want to derive what this regression function looks like. Okay? So what we have here is a sum of 4 separate terms inside of this expectation. So the first thing that we can do is to take that expectation and apply it separately to all 4 of those terms. Okay? The expectation of a sum is the sum of the expectations. Okay, so that's step number 1. Step number 2 is that we can then go through each of these terms individually and figure out what their expectations are. So beta naught is a regression coefficient. It's a constant. We don't know it, but it's a constant. It's not a random variable. So the expectation of a constant, or the conditional expectation of a constant, is the constant itself. So in that step, we've applied that rule right there, okay, using A as the constant. Now here we have the expectation of beta 1, which is a constant, it's also a regression coefficient, times experience, conditional on experience. Okay, so this one here is an example of where we're conditioning. This is like the x, and this is the x here as well. If we condition on experience, then we know experience, we can treat that as a constant. So the expectation of beta 1 times experience is beta 1 times experience, when we condition on experience itself. Now the same thing applies when we have beta 2 times experience squared. Okay, beta 2 is a constant, so it comes out the front, and the expected value of experience squared, given experience, is experience squared. So we're not really doing any averaging. In all 3 of these terms, we're not doing any averaging when we take this expectation. We're simply saying we know experience, and therefore we know experience squared, and therefore we just write it down. Okay? So those second and third terms there are really using this rule here. We're taking the expected value of a term that depends on x alone. And finally we have the expected value of u given experience, and that's 0, so that's disappeared. Okay? So that little operation that we've done there, that little derivation, is the derivation of the regression function associated with this equation that we've written down here. So the regression function is the conditional expectation, and it looks like that. It doesn't seem like much, but that little kind of derivation is something that we'll use a fair bit under different circumstances. All right, here is our last kind of result that we need for the time being, which is the law of iterated expectations. You may or may not have seen this before, but it's a very useful technical tool. And what it says, it seems a bit odd at first, but what it says is that if we have a random variable y and we consider its population mean, then that is the same as taking an iterated expectation. So this is the name, iterated expectations, in this case 2 expectations. On the inside the round brackets, we have the expected value of y conditional on x. So that's a conditional mean on the inside. And on the outside we have the unconditional expectation. So this e here is the same as that e there sort of thing, but instead of having y inside, we have a conditional mean inside. So the way to think about those 2 e's is that the e on the inside is taking an average over the y random variable, okay, conditional on the x's. So you kind of fix the x's at all of their values and take the averages over the y's. And then the outside e is then averaging over the x's. And what the law of iterated expectations says is that whether you do the 2 expectations or the 1 expectation, you get the same answer. Okay? That's not terribly hard to prove. We won't worry about proving it, but we will use it on a variety of occasions. Here is an example. A simple example. Let's suppose we have 2 random variables, u and x. And I've chosen the u and the x notation deliberately because u is meant to remind us of a regression disturbance, kind of like we saw in that wages example just a minute ago. And x is meant to remind us of being like an explanatory variable in a regression. And a typical condition that we assume in an equation like that for a regression disturbance is that it has a zero conditional mean given the x's. Now we can deduce something immediately from this assumption that the conditional mean is zero. We can use the LIE to deduce that the unconditional mean of these disturbances must be zero, okay? Because the unconditional mean is equal to the expected value of the conditional mean, and the conditional mean is zero under our starting point, and the expected value of zero is equal to zero. Okay. So what does this mean? This means that if you have a regression in which the disturbance has a zero conditional mean, it is not necessary to make an additional assumption that the expected value of u is equal to zero. You already know that on the basis of the conditional mean being zero. So it works in that direction. The conditional mean being zero implies that the unconditional mean is zero. It doesn't work the other way around. Okay? If you know or you assume that expected value of u, the unconditional mean, is equal to zero, you cannot be sure that the conditional mean is also equal to zero. You can't use the LIE or anything else to guarantee that is equal to zero. So this only works one way. If you know the conditional mean is zero, that implies that the unconditional mean is also zero. All right, just to continue this, we've said example 2, but it's kind of a continuation of the previous one. Let's continue to suppose that this conditional mean of u given x is equal to zero. Now let's think about the covariance between the u's and the x's. Okay, covariance is at the heart of correlation. So the correlation between u and x is the covariance divided by the standard deviation of the u and the x's. So if we can work out the covariance, then we know something about the correlations. All right, so the covariance formula in the population looks like this: the expectation of u minus expected u times x minus expected x. Okay, that's just the definition, the formula for the covariance. You'll find that in the QM1 notes as well, if you need to refresh your memories. So what does this conditional expectations condition here tell us about the covariance? At first sight, it appears like not much, but we can take some steps and we find that it does imply something. First of all, we already found, just on the previous slide, that the expected value of u is zero when the expected value of u given x is zero. So we worked that out. So the first thing that we can do is we can drop that term. Okay, we'll set that equal to zero. So we've simplified this formula just a little bit. Now, what we'll do next is expand out the brackets so that we have two terms that we're dealing with here. And notice, in addition to that, we've expanded them out and put the e's on both. So e being a linear operator means if we have the expectation of a sum or a difference, then that is equal to the sum or the difference of the expectations. All right, now we can deal with each of these terms here. Okay. Now, the expected value of x, just looking inside of this expression, the expected value of x is a constant. It's a single number. Okay. So remember we illustrated that before when we said the expected value of y when that was adult heights was 168 or whatever it was. This is a number. And because it's just a number, a constant, it can come outside of this expectation right here. So that's what's happened. This constant has come outside of this expectation. So we have these two expectations now taken separately. Okay. This trick here, to take the e of x outside of the brackets, that's not applying here, notice. This term is unchanged. We have a single e over here which applies to both the u and the x. Okay, so this step does not apply over here. But what we're left with is the expected value of u, and again we can use the fact that that's zero to remove that term. Okay, so now that's gone. and we're just left with the expected value of u times x to deal with. So we've simplified the covariance formula down to just this expectation here because of the zero mean of the u, basically. All right, now let's apply the law of iterated expectations, the LIE. We've taken the single e and replaced it with the two e's. Okay. And at first that looks like it's made things more complicated, right? The expression's got longer, but we're going to be able to deal with this conditional expectation in here quite simply. And now we have the expected value of u times x conditional on x. Okay, when we condition on x, we can treat this x as being fixed with respect to this expectation. Okay, so we'll be able to take this x here outside of this expectation. We can't take the x outside of this expectation. This is an unconditional expectation. So this e here averages over the x. So that when we take the x outside, it has to stay inside of these square brackets, inside of this e. Okay, but it can come outside of this conditional expectation. And what we're left with is the expected value of u, conditional on x. Well, that's 0. Okay, that's our starting point. So this is now 0, and therefore we have the expected value of 0. So what we've concluded by that sequence of steps is that if we know or assume that the expected value of u, conditional on x is equal to 0, we have two things. It means that the u's have mean 0, and it means that the u's have 0 correlation with the x's. Okay? That conditional mean implies that the u and the x are uncorrelated. Again, this does not apply in reverse. Okay? If you know or assume that the u's and that the u and the x are uncorrelated, that is not enough to be able to conclude that this conditional mean is equal to 0. Okay, so this this derivation only works the one way, which is okay. We only need it to work that way. So that law of iterated expectations is an important result. It's one that we're going to use quite a lot through through our subject. So if there's anything in there that has gone by a little bit quickly and you didn't quite catch, then I suggest it'd be worth going back and going over it and rereading and just trying to get clear in your minds how that law of iterated expectations is working. It's quite an important result, and we'll see it again very soon.